Okay. Systems of equations. We're going to deal with 2 variable systems and 3 variable systems with this and try to build up to getting those solutions. We're going to use matrix to do this. If you've done some things with a matrix, you're going to be in really good shape. But with any system of equations, no matter how large or how small, there are 3 scenarios that can occur with solutions. One is that it's the best case scenario that there's one solution. That's called consistent and independent. One solution. That means we have one X and one Y. If it's a 2 variable system, we have one ordered pair. That's where those 2 lines cross. Okay. Another case is that you have answers, but you have so many that we can't pinpoint one, and that's an infinitely many solution. The mathy words for that are consistent and dependent. Okay, consistent meaning we've got answers. Dependent meaning they go the same direction. If we're talking about a 2 variable system, we're talking about lines. And if lines are dependent, that means they're going in the same direction right on top of each other. Okay, is what's happening. If they're consistent and independent, they're 2 lines that meet, but they go in different directions. That's independent people go in different directions, independent lines go in different directions. If you're talking about a 2 variable system, which is easier to think of than a 3 variable system. Okay, so consistent means you got answers. Independent means there's one answer. Dependent means that there are infinitely many solutions to that particular system of equations. The last scenario is the no good scenario in which there is no solution. And if consistent means there are answers, no answers would be inconsistent. Okay, inconsistent if there are no solutions. So that you'll see those words sometimes thrown in there. You'll hear me say one solution, infinitely many solutions, or no solutions is what I normally say, just because that's just where I'm stuck at with my vocabulary. But those are the math speak for that. It's consistent and independent for one solution, consistent and dependent for infinitely many, and inconsistent if there are no solutions. Okay, so we're going to go over how to set these up and how to use your graphing calculator to solve them for you. All right, so really easy thing. X plus 4y equals 14. 3x minus 2y equals 0. Okay. There's a system of equations. In a high school math class, maybe an Algebra 1 and Algebra 2 class, your teachers may have had you do processes called substitution or elimination to solve that system, which absolutely works wonderfully. You've got to solve, if you're using substitution, you solve for one of the variables, plug that stuff into the other one, and then you get one equation, one really big equation with one variable, and you solve it. If you're doing elimination, you try to get opposites on the X's or the Y's and cancel and all that fun stuff. That all works wonderfully, and you can do that if you want to. I'm not requiring you to know that. I want you to solve the system, and what we're going to use is a matrix. And in our case, we're going to use an augmented matrix. An augmented matrix is taking these equations and writing it as a matrix. So you're going to have, there's a such thing as a coefficient matrix, which would be the matrix with just the X's and the Y's, or the numbers in front of those. And then there's a solution matrix. An augmented matrix is a matrix that combines those two. The augmented matrix for this particular system is this: 1, 4, 14, 3, negative 2, 0. Okay. 1, from in front of the X, 4 from in front of the Y, 14 from what it's equal to. We've got a column that's X's, a column that's Y's, and then a third column that's what they're equal to. Okay, so when you do a system of equations using an augmented matrix, you need to make sure that you have X's first, then Y's, equal sign, and what they're equal to. So make sure they're in the right order so that you have a column of X's, a column of Y's, a column of numbers. Okay, that the equations are equal to. Okay, what size is this? Anybody remember from maybe knowing something? 2 by 3, 2 rows by 3 columns. So it's a 2 by 3 matrix. Rows by columns is how you name that. Okay, so we're going to need to know that size so that we can put it into our graphing calculator. This is where the graphing calculator comes in. Okay, so pull out your graphic calculator, and we're going to go to the matrix menu. Okay, so to get to the matrix menu, you're going to press second, and then down here, 1, 2, 3, 4 buttons down, that X to the -1 power, right above it, it says matrix. So I'm going to hit that button. I've got some in that I'd already used, but I want to change them. So I'm going to go over to edit. So second matrix, and go to edit. I'm going to edit matrix A. It doesn't matter which one you put this in. I'm going to put it in A so I don't have to go very far. All right. Then I need to change the size of it. I've got a 2 by 3 matrix, so I'm going to put 2 rows by 3 columns. So you just hit a 2 and enter, 3, enter. And it should change what you see there so that you see a 2 by 3 matrix size. Now we've just got to put our numbers in there. So second matrix, over to edit. We're going to pick matrix A. We hit enter. We want to change it to a 2 by 3. Rows by columns. And then we want to put in the matrix that we've written down. Our matrix that we've written down is 1, 4, 14 for the first row. And then 3, -2, 0. So 1, 4, 14. And then 3, -2, and 0. So if there are numbers that are already in there, for some reason you had a matrix already in your calculator, you just type over the top of them and it'll delete them and overwrite whatever you got there. So make sure your numbers are all in correctly. It's kind of like dialing a phone number. 1 digit off gets you a completely different person than the person you're trying to call. 1 digit off in this is going to give you a completely different answer than what you would normally get. Okay, so make sure. All right. Once you've gotten that, we want to hit second and mode to get back to the regular calculator screen. Getting back to normal regular screen. And we want to make this calculator perform row operations on that matrix to the point where it finds the solution. Okay. To do that, we're going to hit second matrix, just like before. We're going to have this thing do math. So we're going to go over to the math menu. We're going to press up, and we're looking for RREF. RREF. That's the command we want, is RREF. There may be another way to get to that using like alpha F1, F2, something like that. I can't remember. I don't ever do it that way. So RREF, hit enter. It pulls that command up to the regular calculator screen and says, okay, what do you want to do RREF to? We want to pick the matrix that we put in. So I'm going to hit second matrix. And then I put that matrix into matrix A. So under the names menu, I'm going to select matrix A. You don't have to close the parentheses, but something in me says I do, so I do. And that creates this matrix. 1, 0, 2, 0, 1, 3. Okay, that's by doing RREF. That stands for reduced row echelon form. If anybody ever asks you, you're on Jeopardy or something, Who Wants to Be a Millionaire, somewhere you're playing that, and they ask what RREF means, you say, ooh, Our RREF is reduced row echelon form. Final answer. Lock it in. Or you phone me and split the money with me. Let's do that. All right, so reduced row echelon form. What does this tell us? This first row tells us that 1x plus 0y's equals 2. So x is equal to 2. The second row tells us that 0x's plus 1y is equal to 3. So y equals 3. You get x and y, 2 and 3. This says x equals 2. This says y equals 3. We have an ordered pair, 2, 3. That's our solution to that matrix. If you take that ordered pair and go back to the equation, 2 plus 4 times 3, 4 times 3 is 12, right? 2 plus 12 is 14. That works in the first equation. I plug in 2, 3 here. 6 minus 6, 0, right? That ordered pair works in both equations. If it does not work in both equations, it is not the answer. Okay? All right. So 2 by 3 matrix, 2 variable system. That's what you're doing there. Okay? Let's step it up a notch. Let's look at this system. 2x minus y plus z equals 0. X plus z minus 1 equals 0. X plus 2y minus 8 equals 0. So this system is a little bit sketchy. Things are not the way they should be. Okay? The way things should be is that I have a bunch of x's in a column, I have a bunch of y's in a column, and I have a bunch of z's in a column. Then I have an equal sign and some numbers, right? If we look back at example A, we had x's first, then y's, equals, and then numbers. Here we got 3 variables. We got x, y, and z. So we should have x's, then y's, then z's, equal sign, and some numbers. So I need to get that done with these equations. Just make sure they're in the right order. The top one, it is in the right order. I got x, I got y, I got z equals a number. Numbers happen to be 0, but that doesn't matter. That it's not a different number. It's a number. That's all that matters. The second equation, I could rearrange by just moving the 1 over by adding 1. And that would give me x plus z equals 1. Technically, there's a what with the y there? Yeah, it's a 0y that's in there. You don't have to write that or anything. Just know it's a 0 for the y. The third equation, well, that 8 should be over there with that 0, so I'm going to move it. Addition this time because it's subtracting 8. So that would be x plus 2y and then equals 8. What's here at the z spot? Another 0z there. So we got some zeros in there. So we're going to set up that matrix. What size should this matrix be? A 3 by 4. 2, -1, 1, 0. 1, 0, 1, 1. 1, 2, 0, 8. That is the matrix that we want to type into our calculator. Is that particular one. All right, so give myself a little space here. All right, 3 by 4. So let's go through putting that into our calculator again so that we get to practice. And so second matrix, go over to edit because we're going to put in another matrix. I'm just going to put it in matrix A, 3 by 4, and then 1, or no, excuse me, 2, -1, 1, 0, 1, 0, 1, 1, 1, 2, 0, 8. Okay. Check your numbers. Remember, 1 digit off gets you a completely different person. So you can't have any of that wrong. If there's something wrong, fix it now so that we don't mess up when we get the answer. Because usually if you don't fix it now, once you hit RREF and get the answer, you probably aren't looking back. Okay? Unless you did not get the correct one of the possible answer choices on a multiple choice. All right. So that's everything's good. I'm going to hit RREF. So second matrix over to math. RREF down there toward the bottom. So I hit up to get there. And I'm using matrix A. And there I get X is 2, Y is 3, Z is -1. So I get this matrix after RREF. 1, 0, 0, 2, 0, 1, 0, 3, 0, 0, 1, -1. That tells me that X equals 2, Y equals 3, Z equals -1. I get an ordered triple, just X, Y, and Z. Yes. The furthest right row is going to be your list of answers, X, Y, and Z. The equal sign is still there, right? Technically, yes. Yeah, that sometimes you'll see this textbook that we're using doesn't tend to use this, but I've seen college algebra textbooks in the past that would put like a line right there saying, okay, there's an equal sign where that line's at. This textbook doesn't tend to do that. I don't hardly ever do that anymore either. So this one would be 2, 3, -1. If you went back to the equations and plugged in that ordered triple for X, Y, and Z everywhere in that, it would all work for you. Okay. We won't do that for this one, but that's what you can do. All right, so here we've seen two scenarios that match scenario number 1, that there's one solution. What does it look like when it's one of the other scenarios? So let's look at that for a couple of problems here so that we can recognize when that happens. Most of the time, you're going to get one solution. That's the most common thing, is one solution. No solution and infinitely many solutions are not as common. In math, we tend to make things work out for us. So we try to give you problems that have one solution most of the time. But we mix in a few of these that don't have a solution or maybe have infinitely many solutions. So let's look at example C. Here's our system. 6x minus y minus z equals 4. -12x plus 2y plus 2z equals -8. 5x plus y minus z equals 3. Is everything in the right order? At XYZ number, XYZ number, XYZ number. We're good. So we're ready to put that in as a matrix. So 3x4 matrix. Put that in your calculator. 6, -1, -1, 4, -12, 2, 2, -8, 5, 1, -1, 3. So let's go do that. So second matrix, and we're going to edit. I've already got a 3x4, so I'm just going to use matrix A and just override all the numbers. So 6, -1, -1, 4, -12, 2, 2, -8, 5, 1, -1, 3. I'll show you a little shortcut with the TI-84s. If you've already used the RREF function, you can just press the up arrow key. If you've got one of the newer operating system ones, especially if you've got a color one, I know it does this, and you can select RREF there, and it says RREF of A. That's the A that we've got in there now. It doesn't remember what the other one was. It just says, oh, go to A and read it. I get that. And I get some ugly answers there. Decimals. So I'm going to change those to fractions if possible. The way to do that with the graphic calculator is math, enter, enter. That's a little better, but I notice kind of an anomaly there. I've got that bottom row. I'm going to copy that to my notes as I can instead of rewriting it. Notice that bottom row. That bottom row is all zeros. The bottom row tells you what's going on. If the bottom row were 0, 0, 1, and then a number, then we've got a solution. Because this bottom row is 0, 0, 0, 0, it's all zeros. That means that there's infinitely many solutions. Okay? All zeros across the bottom row is infinitely many solutions. So that tells me that there's infinitely many solutions. Yes. Okay. So we're going to take those solutions and we're going to write them in terms of a particular variable. Okay. We're going to write them in terms of z, which is the most common way for you to have to do this. Okay. Write them in terms of z. What we have here are some equations. The other two rows are equations. The other two rows give us that x minus 2 over 11z equals 7 over 11. Could I get x in terms of z with that? That means get x by itself. How do I get x by itself for that equation? Yeah, add the 211z. And that's going to give us x is 2 over 11z plus 7 over 11. There's x. The second equation, what's this second row? What does it turn into as an equation? Yeah, y plus negative 1 over 11z or minus negative 11 or 1 over 11z is equal to negative 2 over 11. Could we get y by itself on that one? Yeah, just one move, just add 1 over 11z to both sides. There's y by itself. So, yeah, it's not real pretty, but it's really not that hard to do to get it in terms of z. A little bit more difficult if I ask for you in terms of x. I'm not going to do that. Okay, I'm not that cruel to you. Okay, so here we have y in terms of z. We have x in terms of z. Z is already in its own term. It's z. We're saying, okay, z is the variable. These are what the other solutions look like if we pick any arbitrary z. We pick 4 for z. We could plug it in and get the x and the y values. We pick negative 2 for z. We could get the x and y values that go with that. So your ordered triple looks like this. 2 over 11z plus 7 over 11. 1 over 11z minus 2 over 11. And then z. Everything in that ordered pair, the only variable is the z that I asked for it in. Okay. We'll be able to rewrite your answers in terms of z, which is the easiest of the ways of writing your answers. You go to a more advanced math class, they might ask for it in a different letter, but z's fine with me. Okay. What do we look for on the bottom row to know that it's infinitely many solutions? All zeros. Everything is a zero. Good. Get to the shortest of problems in this particular set of things. X plus y plus z equals 6. 2x minus y minus z is 3. X plus 2y plus 2z equals 0. There's our system. 3x4 matrix. 1, 1, 1, 6. 2, -1, -1, 3. 1, 2, 2, 0. We have that system. Put that in your calculator. Run your RREF. And then we'll see what happens with that. So, graph the calculator, second matrix, edit matrix A. It's already the right size. 1, 1, 1, 6. 2, -1, -1, 3. 1, 2, 2, 0. Oops. Get back to the regular calculator screen. I'm going to go to Math, RREF. Or you could scroll up if you wanted to and get that. Pick up the matrix that I want. I want matrix A under the names menu. Hit enter. Ugh. What's wrong with that bottom row? It doesn't look like the right thing. It's got zeros except for the last spot. So when that's the case, what this says is 0x plus 0y plus 0z is equal to 1. Yeah, 0 never can equal to 1. So that tells us that that's not true. 0 can never equal 1. So that means that this one has no solutions. And we don't have to do anything else because there aren't any solutions to write about. No solution. That's our favorite ones, but they occur the least amount of times. So, dang it. You could, but it won't be from me. Yeah, at least you try. That's a good question. Just to give quizzes like that? Yeah. So what you do is make all the answers C. That I have done. That I have done. And that's impossibly wrong. Yeah, I always do that because I have like the honor students in my high school in my dual enrollment classes there. So it always makes them nervous when they get 2 or 3 that are the same letter in a row. So I just made them all A or all B all the time. The look on their face is priceless. I love it. It's so funny. But yeah, it's quite a funny thing. So yeah, no, it would make you guys nervous too. I promise. All right. Okay. Let's look at one other thing while we're talking about your calculator doing row operations. Let's talk about how to do a row operation by hand because they always ask this on the final. Always. They ask you to do a row operation on the final. Okay, so I want to show you how to do that. It's really one of the easiest things ever. So if you're asked to do a row operation, they never ask you to do row operations and show how to solve one. Solving, you just do the RREF and go from there. But they do ask you to say, okay, here's your original matrix is this, 5, 2, 13, -3, 1, -10. They give you a matrix, and they say, perform the following row operation. Row 2 is equal to 3 times row 1 plus row 2. Notation-wise, what that means is row 2 is the only one that's changing. Okay, row 2 changes. It changes by doing this. We're going to take 3 times whatever's in row 1 and add it to the same place in row 2. So for our problem, we're going to take 3 times 5 and add it to the -3 that's here. Okay? So after that row operation, you're going to get another matrix back. Which row changes according to that direction? Row 2. So that means row 1 does what? Stays the same. So copy it down. Row 2 is the only one that's changing. Okay? So we're saying 5 times 3, because it said 3 times row 1. So 5 times 3 is 15. What? Positive 3 times positive 5. So it's positive 15 plus negative 3 would be 12. So row 2 has 12 in that spot.
You're not multiplying it by the 5 and negative 3.
No, I'm multiplying. This 3 is multiplying to this row only. It's kind of like distributed property. Yeah. And then I'm saying, okay, 3 times this 2, 6. 6 plus 1 is, so a 7 goes right there. Okay. And then 3 times 13 is 3 times 13? 39. 39 minus 10 would be 29. And there's your new matrix after that particular row operation. That's the thing your calculator is doing. When you do RREF in the background, it's doing a lot of algorithms to get the matrix into that ones and zeros kind of format. It's doing a bunch of those. They always ask something like this on the final. When you see the practice finals this week, when you get those, when you look through for problems like this, you're going to see one that says do this row operation, and what's the result? This is what they're asking you to do. It's one of the easiest things in the world. It just looks like you're doing rocket science. You're not. Yeah. If math can make you feel cool, that's it. All right. Let's go to the next section, 12.4. Skip it. Yeah. Matrix algebra. And operations. It's easy. Super easy. All right, so we're going to have 3 matrices that we're going to write down here. Matrix A is 3, 6, 5, -7, 2, and 10. Matrix B, 1, -2, 11, 8, -5, 14. And matrix C, 6, -4, 2, -1. Okay. Now, we're going to do some matrix operations first, and then we'll get to some of the algebra-ish things that we do here. But operations will be what we do first. Really easy thing. Okay. Matrix operations are similar to just arithmetic operations, like add, subtract, multiply, divide. But we don't divide with matrices. We only add, subtract, and multiply. Okay. We never divide them. So we're going to add, subtract, and multiply. The rules for addition and subtraction are different than the rules for multiplication. Okay, to add or subtract matrices, addition and subtraction must be the same size. Matrices, which is the plural for matrix. To add or subtract, they got to be the same size. Okay, so with these, what size is matrix A? 3 rows by 3 by 2. 3 rows by 2 columns. Matrix B, what size is it? 3 by 2. Matrix C, 2 rows by 2 columns. Okay, so which of these two could I add or subtract? I could add A plus B. I could add B plus A. Same thing. But I could not add A and C or B and C because they're not the same size. Okay, so to do that matrix addition, A plus B. Let's do that one. The way that works is you add corresponding parts. So they got to be the same size. So if this is a 3 by 2, this is a 3 by 2, they both got to have a top left, right? So to add them, the top lefts add together. 3 plus 1. 4. So the top left of that one, we're going to get one that's the same size back. We're going to get a 3 by 2 back. So it's 4, 6 plus negative 2, 4, 5 plus 11, 16, negative 7 plus 8, 1, 2 plus negative 5, and then 10 plus 14, 24. So we get a 3 by 2 back. Can you do that in the calculator? Absolutely. But why would you? You just enter those two matrices in your calculator, and then you would using the names operation, you would go to second matrix. You would pick up matrix A plus second matrix, and then after you had entered in matrix B, and then hit enter, and it would crank out that exact matrix that we've got right there. I don't usually do addition in the calculator just because by the time I've typed it all in, I could have just added the numbers myself. Okay, it just takes me longer to type them. You may feel more comfortable doing that with the calculator, and I'm fine with that. It doesn't matter to me. Okay. Subtraction, same rule. If we did B minus A, 8A, okay? It's got to be the same size in order to subtract. So we start with 2 3 by 2 matrices. We should get a 3 by 2 back. All right. So B minus A, 1 minus 3, negative 2. Negative 2 minus 6, negative 8. 11 minus 5, 6. 8 minus negative 7, 15. Negative 5 minus 2, negative 7. 14 minus 10, 4. You get that matrix back. Again, you can do that in your graphing calculator, put in matrix A and B, and then recall the names with the operation between them, and that works just fine. If we tried to add matrix A plus matrix C, that doesn't work because they're not the same size. The answer to one that when it doesn't work is undefined. That's because they're not the same size, they're undefined. If you try to do it with your calculator, it's going to give you an error and say dimension mismatch, which is the reason you can't do it. If the dimensions aren't the same, you can't add or subtract them. Okay, so dimension mismatch is what that's called. But undefined is what your answer is going to be. All right. So there's addition and subtraction. Easy thing. Super easy. The next thing is scalar multiplication. Scalar multiplication. Let's use a matrix A. Let's call it 2, 6, negative 7, 8, 5, 3. Scalar multiplication is taking negative 3 times matrix A. This one, we kind of referenced it when we were talking about row operations. And somebody said it's like distributed property. Well, it's not as much like distributed property as scalar multiplication is. Scalar multiplication is exactly distributed property. It's distributing whatever you're multiplying times that matrix to every piece of the matrix. So it's negative 3 times 2, negative 3 times 6, negative 3 times negative 7, negative 3 times 8, negative 3 times 5, negative 3 times 3. So you're just really are distributing whatever number is here to every element inside of the matrix. Okay? All right, so that would give us negative 6, negative 18, positive 21, negative 24, negative 15, and negative 9. Scalar multiplication. Scalar multiplication can also be used in matrix operations combined with addition or subtraction. So you might have a problem that says 2A minus 4B. And you're supposed to work that out. Let's use matrix A and B from the top. So if we're looking at these two matrix A's and B's up here, 2A minus 4B. 2A means you double everything in A. 4B means you multiply everything in B by 4. So 2 times 3 is 6, minus 4 times 1, 2, right? Okay, so we're going to get a 2 back. Okay. Our matrix, be a 2 right there. And then I'd say 2 times 6 is 12, minus 4 times negative 2 is negative 8. Oops, sorry. That comes back. So 12 minus negative 8 be 12 plus 8, which is 20, right? And then 2 times 5 is 10, minus 4 times 11 is 44. Be negative 34. 2 times negative 7 is negative 14. Minus 4 times 8 is 32. 14, negative 14 minus 32 be negative 46. 2 times 2 is 4. Minus 4 times negative 5, which is negative 20. 4 minus negative 20 is 4 plus 20, which is 24. 2 times 10 is 20. Minus 4 times 14. 4 times 14 be 56. So 20 minus 56 is negative 36. Now, I did that all in my head without typing that in the calculator. I don't expect you to have to do that. If you want to put it in the calculator, I mean, if you're not comfortable doing that arithmetic without that, I'm fine with that. I would go to my matrix, go over to edit, matrix A. I put in that 2 by 3. No, 3 by 2 is what it was. 3 by 2. For matrix A, I had 3, 6, 5, negative 7, 2, 10. And then I'd go to matrix, get out of that, go to back to the matrix, go to edit, and I'd go to matrix B. And I'd put in that matrix. 3 by 2. 1, negative 2, 11, 8, negative 5, 14. And then to get your calculator to crank out that 2A minus 4B, you say 2 times matrix A minus 4 times matrix B. Enter. And we get exactly what I got by doing my hand. But you can get the calculator to do that for you. It'll still work. If you just put 2 and then matrix A minus 4, then the name, it still recognize that as the times. I guess out of habit, I just put the times. That way, when you look at that screen, you'll know, hey, he was multiplying there. I guess that's just out of habit. But you don't have to put that in there. It'll still recognize it. Good question. Okay. Scalar multiplication, addition, subtraction. Fairly straightforward. All right. Next thing in the same section is multiplying matrices, which is not quite as easy if you want to do it by hand. I used to be really good at this. I'm not as good at it as I once was because I don't do it very much. So when you name the size of a matrix, it's row by column. How many rows is it? How many columns is it? When you multiply two matrices, you got a matrix 1 and matrix 2, two different matrices. In order to be able to multiply them, these two have to match. If they don't match, you can't multiply them. The columns from the left matrix must match the rows from the right matrix. Yes, by match, I mean be the same number. So if the first one has 3 columns, the one on the that you're multiplying it to on the right has to have 3 rows. Okay. So example being, like if you had a 2 by 3, in order to multiply it's got to be a 3 by something else. It could be a 3 by 4. What that results in, because those numbers match, the answer to that, the size of that matrix will be 2 by 4. And that comes from these numbers on the outside. That's where that's coming from. Okay. So columns on the left one got to match rows on the right one. The outside numbers on the dimensions are going to be the size of your answer. Okay. All right. Let's do a little bit of matrix multiplication. And I do not expect you to do this by hand, honestly. You can. I don't expect you to. Matrix A. 2, 4, -1, 5, 8, 0. Matrix B. Let's make it a pretty big one. 2, 5, 1, 4, 4, 8, 0, 6, -3, 1, -2, -1. All right. What letter we're on here? F. Is that right? F. All right. So we got our 2 matrices there. If I'm going to say matrix A times matrix B, first thing I need to decide is, can I even do it? What size is matrix A? 2 by 3. Good job. What size is matrix B? 3 by 4. Okay, so our matrix, the 2 numbers in the middle, match. So that means we can do this. And we will end up with a 2 by 4 as the result. Okay. The way that you would do it by hand, and I'm just going to talk this, I'm not going to actually write it because I don't expect you to do this by hand, is you take the row times the column. 2 times 2 is 4, plus 4 times 4 is 16, is 20, plus -1 times -3 is 3, that's 23. So the top left of our first row is a 23. And then I take that row times the next column. So 2 times 5 is 10, 2 and 4 times 8 is 32, so that's 42. -1 times 1 is -1, that's 41. So you'd have 23, you'd have 41. And then you do the next row, that top row times the next column. And you keep doing that until you got them all done, until you got your 2 by 4 place done. Okay, so the top row of the left matrix times each column and add the results of the corresponding spots. It's not, like I said, not what I expect you to do by hand. If you go to engineering, if you're going to be an engineer or whatever, and you take a linear algebra class, you are going to have to do this by hand. Learn it then. If not, I don't see any application to this for the rest of most of your lives. So, but if you are going to engineering school, you might want to work on maybe learning to do that by hand. 2 by 3. All right, so I'm going to enter in matrix A, 2, 4, -1, 5, 8, 0. Okay, so there's matrix A. Go enter in matrix B. It's a 3 by 4. 2, 5, 1, 4, 4, 8, 0, 6. -3, 1, -2, -1. Okay. So there's matrix A and matrix B are in there. I'm going to tell my calculator to multiply them. So matrix A, enter, times matrix B. And this is one of the cases where I would put the multiplication symbol. I think most of the time it will do it without the multiplication symbol. I don't ever chance it. I always just put it in there. That way I know where I got that. So 23 and 41, that was the numbers that I told you that I found by doing it by hand. But 23, 41, 4, 33. That's multiplying that stuff out. Get that matrix right there. 23, 41, 4, 33, 42, 89, 5, 68. Like lottery numbers, I guess. Play that and see what you win. You got to pay me if you win something. That's
Winning numbers.
That's not ironic at all, is it? That's funny. All right, so matrix multiplication. Calculator. Matrix multiplication is not commutative. So don't put in, if it asks for matrix A times B, you cannot put in B times A and expect the same result. That's one of the things with matrix operations. It is not commutative across multiplication. Addition and subtraction, or addition, it is. Subtraction is not commutative anyway. But multiplication, it does matter what order you type it in there. Left matrix, right matrix matters. Okay? All right. One more thing in this section. Inverse matrix. When I say inverse, I don't ever say, you never say this with matrices because there's no such, I guess there's not such a thing as an additive inverse matrix. I guess there is, but there's no point in it. But it's a multiplicative inverse. And if you think about it in that terms, it makes the idea of what you're doing make more sense. What's a multiplicative inverse of, say, the number 3? It's 3 to the negative 1 power, which is 1/3. That's what an inverse does. It's a reciprocal. So with a matrix, what we're trying to find is the reciprocal matrix, basically. And it's not as easy as just flipping all the elements. That would be too easy. It's not that easy. Okay? We're not going to do it by hand. That takes lots of row operations and patience. And if you mess up on step 2, then your step 30 is useless. So, yeah, some of them take a while to get that way, depending on your route and what order you do things in. It's kind of like Rubik's Cube solving. If you know how to do it, you can take shorter routes than people that don't know what they're doing. Yeah, and there are algorithms for all that will automatically solve them. That if you just memorize those, you will stumble into the solve portion at some point with those. So if you know those and you can do those quickly, you can really seem like a genius. And it does take a good bit of smarts to memorize those, no doubt. But inverse matrix, all it takes is a calculator. That's what we're going to do. So here's a matrix. We'll call this matrix A. 1, 1, 0, negative 1, 3, 4, 0, 4, 3. That's our matrix. To find the inverse matrix, we're looking for A inverse, which is that notation. A to the negative 1 power is what that looks like. Put that matrix into your calculator. Notice that it is a square matrix, meaning that it has the same number of rows as it does columns. It has to be invertible. It has to have that size, same rows, same columns. And then just put them in there, okay? So we're going to put that matrix in the calculator. Second matrix, edit, matrix A, 3 by 3 this time. 1, 1, 0, negative 1, 3, 4, 0, 4, 3. So get that matrix put into your calculator. And your calculator has an inverse button. It's the same button we've been using to go to the matrix menu. Right, it's that x to the -1 power. It's right here where it says matrix there. I'm going to hit it so it turns red. It's that button right there. So what we need to do is pick up the matrix we want to invert. So second matrix, we're inverting matrix A. Is the one I put it in. If you did a different letter, you pick that one. And then I'm going to hit the inverse, which is this button right here below math. And it's that notation, matrix A, inverse. Hit enter, and it gives you this nice decimally thing here, unless you have your calculator set to give you fractions automatically, which you can if you want to. I don't ever do that. So, but I'm going to hit math, enter, so it turns it into fractions for me. And there is the inverse matrix for matrix A. Be able to find the inverse matrix for matrix A. Yes, sir.
Is there like a kind of system of equation problem where you need to multiply it, like a matrix by the inverse of another matrix?
Yes, absolutely. I'll draw one up in just a second to show you exactly what's the use in the inverse matrix. It does work really well for solving a system of equations. I'll show you that in just a second. So there's our inverse. So I'm going to copy that to my notes. There's inverse matrix right there. That guy right there. That's my inverse matrix. Now, what Dakota was saying there is you got, if you had a matrix A times a variable, and it might be equal to some numbers like 7, 6, -2. This matrix that's here might have some numbers in it, something like 1, -2, 5, or let's just make it our matrix that we've got here: 1, 1, 0, -1, 3, 4, 0, 4, 3. 3 looks stupid. Okay. That would be a system of equations. And if you ever do any vector math, this is kind of the vector notation for a system, is that you've got these sets of vectors that has an x vector, a y vector, a z vector, and then you end up together, they form this, I guess what's the best way to say that, a transformational vector that looks like this, whatever application you're using this with. Okay. What you do is you take the inverse of that matrix and multiply it on the left of each side to solve that. That would be the, if you've got A times some matrix and it's equal to some solutions, so we call them A, B, and C. To solve that, you take A inverse times A, X, Y, Z, and then A inverse times that matrix, A, B, C. And what that gives you is the answers for X, Y, and Z. That's what happens. That's what that application of the inverse is. It's just like an equation. If you had 3x equals 15, in Algebra 1, we teach you to divide by 3. If we think multiplicative inverse, what's the multiplicative inverse of 3? 1/3. If I multiply by the multiplicative inverse of 3, what's it get me? It gets me x back, right? Which is the answer. That's the same thing we're doing here, except for our multiplicative inverse is a matrix. It's just a bigger picture thing. It's a much more complex problem out of that. I've seen this before as a kind of a question in a final exam. I've seen that kind of scenario before. It's been a couple of years since I saw it, so I don't know that they ask questions like that, but I'm glad you asked about it because it does come up.
A couple of weeks ago in Algebra 2, I think the same time, we did the basics of matrix. And you gave us a bunch of word problems, like they were all based around like selling things for a certain amount.
Yeah.
And we used this to solve it.
Yeah, that'll do it. Or you could have used the RREF. That gets you the exact same answer.
Are we going to have many word problems on the final?
On the final exam, yeah, possibly. Yeah. That happens. All right. Yes, ma'am.
What if you're asked for inverse of something that's not like the 35 degree?
You can't.
You can't.
It would be an undefined. So it'd be, yeah, if it asks you to find the inverse of a non-square matrix, you can't do it. It's an undefined thing. Good question. All right. Bye-bye matrices. We're done with you. Let's go to something else. Okay. 12.6. I'm skipping over to 12.6. Doing nonlinear systems. And we're gonna again rely on the calculator a lot here. Okay. Here is a nonlinear system. There's a linear equation. But its other equation that's part of the system is 2x squared minus y equals 0, which is not linear. So that makes this a nonlinear system. Okay. Nonlinear systems are not as easily solved as linear systems. The matrix things that we've done to solve those systems, those are linear systems. Okay. Nonlinear systems have curved graphs. What do we know about the graph of something that has x squared in it? It's a parabola, so it's a curve, obviously. So if it's a curve, then that means it's not linear. We can't use a matrix to solve it. So if you see a system of equations that says solve, make sure it's linear, doesn't have exponents first. If it has exponents, you can't use a matrix. If it doesn't have exponents, you can. Here, we got exponents. This is what I would do to solve them. This is how I want to show you how to solve them. And that would involve taking each equation and getting y by itself. So if I solve this first one for y, that would be y is equal to 3x plus 2. Just by subtracting 3x and then dividing everybody by -1. I get 3x plus 2. The second equation, I subtract 2x squared and then divide by -1. And I'm going to get y is equal to 2x squared. I'm going to graph both of those. My calculator. We'll go to y equals. Make sure in your y equals menu that you don't have any of your plots on. If one of those plots is darkened in, if you hit y equals and you get there and it looks like that, then you need to press the up arrow and get to that plot and hit enter to turn it off. Okay. Make sure your plots are turned off. And then put in those equations. So we got 3x plus 2 and then 2x squared. I'm going to hit graph. There's the linear equation. And there comes the quadratic. What we need is the solutions to this. How many solutions are there to that system? 2 real solutions because it crosses in how many places? 2. Let's get a good decimal approximation for where they're crossing. Okay? And the way to do that is using one of the tools on the graphing calculator. This is not a program. This is not a cheater way of doing it. It is the part of the graphing utility here. So to do that, you're going to hit second trace. And where 2 lines cross is also called a what? Intersection. So we're going to use the choice number 5 for intersect. Okay. The first curve, I've got it on the blue one. I'm going to go to the left of where it is. I'm going where they're crossing the first time, and I'm just going to hit enter. And on the second curve, I'm just going to go to the right of where they cross. It doesn't really, it's not necessary, but I always just do that because I think it helps. Then it asks us to guess. And that's because the reason you want to guess is because you can't get them both at the same time. You got to get one and then the other. So when it asks you to guess, you need to move your cursor close to where you think they cross. I think it's pretty close to right there. So I'm going to hit enter. And I was really close. So it gets me that one, negative 1/2, positive 1/2. That's an ordered pair, negative 1/2, positive 1/2. I'm okay with using decimals for that. That's not a problem. Okay. I just converted it to a fraction because it was easy. Okay. Now I need to find that other intersection. Whoops. So the other intersection, you're going to hit second trace. In the calculate menu, we're going to pick intersection. First curve is the blue one. I'm just going to get up there close to it so I don't have to move around so much later. Hit enter. Second curve. I'm just going to move up there closer to where they're crossing. Hit enter. And then it asked me to guess. So I'm going to get close to where I think they cross, which is about right there. And it says it's at 2,8. Nice little intersection there on a nice integer value, 2,8. 2 places it crossed, 2 ordered pairs. So your job is to get y by itself on each of the equations in a nonlinear system and graph it. If you do that, then that allows you to find the intersection of those 2 graphs. That one was fairly simple because we had one linear equation and one that wasn't linear. Let's look at one where both of them are not linear. Okay. It doesn't get much harder, though. I'm going to promise you that. You just got to do a little bit of algebra first. X plus y squared, x squared plus y squared equals 13. And the second equation is x squared minus y squared equals 7. If you know much, if you've ever had conic sections in, maybe you took pre-calculus in high school or something, or maybe your algebra 2 teacher was an overachiever and got to this, and where nobody else in the state does. So the first equation, I know that that's a circle because it's x squared plus y squared equals a number. Do you have to know that? No, but it is kind of helpful to have an idea. The second equation is not a circle because it has a minus sign in the middle of it. That's actually a hyperbola is what that's called. And it's this kind of, it almost looks like an X, but the graphs look kind of like my arms do right now. They do like that. So what we want to do is get y by itself on each of those. So if I work with the first one, I'll get y squared is equal to negative x squared plus 13. But y is not alone. What do I have to do to get y by itself on that first? Take the square root. And if I take the square root in a problem, what do I have to put in front of it? Plus or minus. And that's where we've got to have that for the graphing calculator. Because this is 2 equations. That right there is going to give me an equation where it's y equals the positive square root of that stuff, and then y equals the negative square root of that stuff. So it's going to take us 2 equations on the graphing calculator to get that one circle drawn. Okay, so let's get the other equation, y by itself, so minus x squared, negative y squared equals negative x squared plus 7. I'm going to divide by negative 1. That's y squared equals x squared minus 7. Then I do the same thing. I'm going to take the square root. Y equals plus or minus the square root of x squared minus 7. Okay. Then I'm going to take those equations and I'm going to put them in the graphing calculator. So I'm going to go to y equals, clear out this other junk that I had, square root. So I'm going to do the positive side first. The square root of negative x squared plus 13. Negative x squared plus 13. And then right underneath that, I'm going to do negative square root of negative x squared plus 13. I'm going to graph that and I'll show you what that looks like. It's almost a circle. Because the way the screen resolution is, if I hit zoom square, it'll fix it to make it, that's more of a circle. The resolution gets too narrow right here. These lines actually continue. If you zoom in, you'll see them connect. But the resolution gets too tight right there and you just can't show it. But that makes a circle. That's what that does. All right. Now, let's go back to y equals and let's graph the other equations. So the positive square root of x squared minus 7. And then the negative square root of x squared minus 7. Here's the positive side. Here comes the negative side. How many intersections do I see? 4. So that means I've got 4 solutions to this nonlinear system. How do I find any of them? Little thing I did earlier. Absolutely. That is the best way to do it. Okay. So I'm going to hit second, trace, intersect. First curve is the blue, the top half of the circle. Second curve, I'm going to press the up arrow until I get to the black one. Or, yeah. Enter, and then I want to. All right, ask me to guess. Come on. Oh, I got to trace it around until I get it. Hang on. All right. Graph. There's my stuff. Second, trace, intersect, 5. All right, first curve. I'm going to get over here close to where that first intersection is there on the top left. Second curve, I'm going to press the up arrow until it's on the right graph, which it is there. Okay, there's it following the correct graph, which is that black part of that curve there. All right, so hit enter. I want to guess, where is it close to where they cross? Looks about right there. Hit enter. And there's that intersection. Negative 3.16 and positive 1.73. Negative 3.16, 1.73. Their decimal approximation is absolutely fine. What I'm looking for. Okay. And then do it again. Second, trace. 5 for intersect. First curve. I'm going to move over here. I'm going to get that one on the top right. I'm going to get over there close to it. Oops, too far. Back on there. There you are. All right, enter. Second curve. I'm going to press the up arrow until I'm on Y3. So I'm following the right one. Press enter. Guess and get close to where I think they cross. Positive 1.36 or 1.16 and then positive 1.73. There's one answer. There's 2 answers. Let's find 3 and 4. And they're the intersections of Y2 and Y4. Second trace, intersection. So I need to get to Y2 and Y4. And right there is pretty close. 3.16, negative 1.73. And I can go ahead with pretty good confidence and estimate that is exactly the opposite sign on the other side there, because we look at that graph, it's easy to tell that it's really symmetric, and it matches up. Fold it. It's symmetric about the X and the Y axis. Pretty neat. Kind of looks like a baseball if you get all the curve in there. Just baseball season, my favorite time of year. All right. 12-6. Be able to do that kind of stuff. Not going to be just incredibly difficult on you, but make sure you can crank out some stuff like that. All right, so let's look at 12-7 and 12-8. 12-7 is systems of inequalities. Systems of inequalities. Let's say we had y is greater than 3x minus 7, and then y is greater than, we can open this up to linear or nonlinear. I want to do nonlinear here, so let's do x squared minus 5. A system of inequalities. We're going to graph to solve. So the answers to this is the whole graph. Okay. Now, what does the graph of y is greater than 3x minus 7 look like? Just a rough sketch, and then we'll do it with the calculator. Well, I go down to -7, and that's my y-intercept, and I go up 3 over 3, or up 3 over 1, and here's the difference in it and a regular equation. It's going to be a dotted line because it has no equal to mark on the inequality symbol. And then it's greater than, so it's going to be above it. The shading is going to be above it. So my shading would be in this direction because that's above, because it's greater than. If it were less than, the shading would be below, which is this way. Okay. Does that make sense? All right. Now, what's the graph of this thing look like? Curve, parabola, right? Well, where does it start at?
-5.
-5 on the y-axis. Okay, so I'd go down to -5 on the y-axis and put that, and it's going to open up because it's a parabola with a positive in front of x squared. It's going to be a solid line because it's got the equal to mark. So it'd be somewhere around there. That's -5. And it would go up something like that. Right? Greater than that would be above, right? Above this line is on the inside of the parabola. Greater than on a parabola that opens up is inside. Less than would be on the outside. So think about the vertex there. If it's greater than the vertex, it's up here. It's less than the vertex, it's down here. So that's inside or outside. So this is inside. So the shading would be in there. So if I use the blue, that green area there, all of that overlap is the solutions for that. If we graph this with the graphing calculator, I want to show you how to do that without using a program. I know there are programs that you can download that do inequalities. I don't use them because technically they're prohibited on ACT and UTM mathematics. So we're going to do 3x minus 7. And here's what we're going to change. We're going to go press over to the left until we see that line. And if you've got the newer one, one of the color ones, if you hit enter right here, it's going to give you options. And I want to change it to the circle or to the little triangle that's toward the top. If you've got one of the other ones, the older ones, you're going to press enter. Just press over till you get that, and just press enter until it's that picture with the little triangle in the top corner. Like that. So press enter until it turns into that. And then let's look at the graph of it and show you what it looks like. Should look like our picture. And it does. Okay. Only thing you can't really tell is that it's a dotted line, which is just impossible to do on the graphing calculator. Okay. Now we need to get that parabola in there. So y equals, we got x squared minus 5. And we're shading a greater than on it, so I want to change that shading to the same thing, the little triangle on the top. Click OK. And the graph. And here it comes. Very similar to what I drew by hand there. Okay. The answers are in that purplish looking area there. Okay. Overlap is where the answers are. How can you check that? Like say you've got a test in front of you and there's 4 graphs already drawn. How can I tell which one's the right one? Pick an ordered pair from the overlap area and plug it in to both of the inequalities. If it works in both of them, it's true, then that's your solution area. Okay. Any ordered pair within the overlap region should work in both inequalities. So it's very easy to pick the right one out of that anyway. Okay. All right. Last thing for Math 140 for the entire semester. I'm going easy on you here for linear programming. I'm not going to get into it too deep. I don't want to punish you here at the end. You made it this far. So linear programming. I'm actually not going to give you the word problem and say find all of the restrictions and constraints and all that stuff. I'm actually going to give you the graph of the constraints already done. Okay? So you would get a graph that looks something like this. And it would have, might have a red line here and a blue line here, and then some diagonal line doing something like this, and then all the shading that happens with that, and you end up shading this area is the overlap of all of those inequalities out of that. That's what happens. Okay. And that area is the overlap of all the inequalities, the constraints, and there's ordered pairs here. So let's say that ordered pair is 25. This ordered pair is 25, 0. This ordered pair is 15, 0. And that ordered pair right there is 15, 5. I'm actually going to give you all of that fun stuff already done for you. What you have is what's called an objective equation. They give you this objective equation, and I use Z there. They may use I, they may use M, they may use a different letter. But X and Y comes from these ordered pairs that are the corners of that graph. The corners of that overlapped constraint graph are what we're going to use to either maximize or minimize the objective equation. If I maximize it, I'm looking for what kind of number? Big or little? Biggest, right? If it's a maximum, it's the biggest. If it's a minimum, it's the smallest. So I'm going to check that for each ordered pair. So for 15, 5, Z would equal 0.02 times 15 plus 0.03 times 5. And I'd get that number, 0.45. Okay. And then I'd plug in 15, 0. And it doesn't matter what order you put the ordered pairs in, as long as you do all of them. So 2/10 of 15 be 0.0 or 0.3, and then 25 0.02 times 20, 0.03 times 5, 0.15 plus 0.40 is 0.55, and then 25 zeros the other ordered pair. So I'm getting every corner of that constraint polygon is what they call that. So 25 0.03 times 0. So be 0.50. The maximum is 0.55. That's the biggest one, right? At the ordered pair 20,5. The minimum, what's the smallest? 0.3. At what ordered pair? So whether they ask you to maximize or minimize, that's what you're going to do. Okay. Again, I'll give you the graph, the corners, and all that stuff, and the objective equation. And all you got to do is maximize it or minimize it. Okay. Not a difficult thing. Okay. All right. So that ends our material for college algebra, Math 140, for spring 2018. You have Canvas quiz this week. You'll have exam next Monday, 4 o'clock, just covering chapter 12, stuff we've done, okay? Just covering chapter 12. This week, things to look for on Canvas are your quizzes, a review for chapter 12 test, and then 2 reviews for the final exam. I'll put those out there, okay? That we'll have a key, the reviews for the final exam will have a key with them so that you can check as you're going there, and we'll get ready to take this final, which is on April the 30th at 4 o'clock, okay? And then I'm not sure what we have to do there. I'll email Dr. Deere. Yeah, you asked and I'll ask too, and we'll figure it out. That's not a problem. But so if you did not get your test paper back, it's right over there if you took it. So, and if you want to take a picture of the key so that you know what you did right or wrong there, if you want to use your test to study for the final, you can. Okay.